Yeah, welcome everyone. So today we have amongst us Professor Ujjwal K. Gautam. He works at the Indian Institute of Science Education and Research, Mohali. He's leading the Nanomaterials and Energy Group there, which is an interdisciplinary research group inspired by the opportunities arising from a confluence of global trends in energy research and environmental challenges, leading to fast growing scientific breakthroughs and market opportunities. So his research work focuses on developing functional nanomaterials and their applications in energy harvesting and environmental remediation. This primarily involves looking at photocatalysis, electrocatalysis, in situ investigation of reaction kinetics, exciton dynamics, X-ray diffraction based structural analysis, surface characterization techniques, and high resolution structural analysis using electron and atomic force microscope. His group is interested in developing chemical routes for highly monodisperse, shape-controlled nanocrystalline semiconducting and metallic catalytic materials that can either split water with the help of sunlight to obtain hydrogen that stores solar energy in the form of chemical energy of conversion, or reduce oxygen efficiently, enabling it to form oxide ion and hence combine easily with hydrogen even at room temperature, leading to the release of stored energy on demand. Importantly, in this energy strategy, water is generated as the only reaction byproduct, which is environmentally benign. And based on similar principles, they are further examining the oxidation of small biofuel molecules such as alcohols or nanocatalyst surfaces. So the fundamental aim of his group is to find a cost-effective method to produce fuels using only sunlight, water, and carbon dioxide. So this was motivated yesterday in the main theme as how we can really have a sustainable development when we primarily look at sunlight as one of the important sources of energy. So his group has done significant progress in this area. So one of his key contributions also involves exploring weak interaction based self-assembly and shape control. So in the emerging field of organic and carbon based semiconductors, fullerenes are unique for their excellent electron accepting nature. They exhibit the ability formation, imparting fascinating properties such as high electron mobility and enhanced luminescence. As another of his research interests, he works towards understanding the chemical interactions involved in such solvates and effects on their electronic properties. He is looking at the shape control of self-assembled fullerenes with an intention to address some of the very fundamental issues related to shape control and nucleation. Professor Gautam completed his PhD from JNCSR Bengaluru and did his postdoctoral work at the National Institute for Material Science, Tsukuba, Japan. Among his hobbies, he is fond of martial arts and cooking. Yeah. So Professor Gautam, over to you.
Thank you, Ajay, and it's a great pleasure to join you. And yeah, as Ajay said, I think my interest is martial arts, but only watching movies, not really. So when
So
we're in
Professor,
Japan,
Professor Gautam, you can share the slide. You can share the slide.
okay,
Yeah.
okay, I was just talking. So how much time I have?
Yeah, please
Do I
go
have?
ahead. Please go ahead.
How much time do I have? Ajay, am I audible?
As you wish, sir. Please go ahead. Yes, you are
Okay.
audible. As you please, sir. Please go ahead. You were
Okay.
telling some anecdote. It looks like. Yeah.
Yes. In case there's a breakage in my voice,
No, no.
please let me know. I'll
Okay.
change the internet
Okay.
source.
Okay. Actually, our schedule is 7 to 9.
Okay. So I think I'll try to finish by 8, and then probably we can
Then
discuss.
we interact. Yeah.
Yes, what I was telling is that a couple of things. I did my PhD work in JNCSR, but my official affiliation was with IISc. So as per my certificate, I'm basically from IISc. I'm a IISc student from SSU department. So I finished in 2006, and in fact, then I went to Japan, and at that time for postdoc, and I met Ajay for the first time. So we are good friends. And then Ajay knows that I used to go and take some martial arts
Yeah, Professor
classes.
Gautam, I'm sorry. Like I think I mixed up JNCSR and ISC.
But you did an amazing job. I mean, the introduction that you gave is, I would like to keep it actually. It was wonderful. Thank you. So, right now, last about 7 years, I'm working in Mali, and we work in different fields. I am from chemistry background, and I started my career by developing different functional nanomaterials. So when we started our PhD, at that time only synthesis was the important thing. I mean, other things were not that prominent at that time. And but as the field progressed over the last 20 years, we started exploring their different uses. Last 7 to 8 years, we have been exploring their use for catalytic applications. As you guessed that this is it's very suitable for a chemistry department, and is also backed by my background. So and also this, I think this lecture series is related to sustainability, and we're making a conscious effort uh, that our research is related to sustainability. So today I'll be discussing some of the very recent developments from our group, uh, which is involving waste plastic. That the motivation is that if we start off with plastic, and because my background is nanomaterials, can I convert it to some nanomaterials and then make a nanomaterial which can be used for energy harvesting, or again environmental remediation. So I'll I'll try to keep this talk mainly non-technical, but please feel free to stop me in between if somebody wants to, and if required, we can also talk otherwise at the end. So so first, I'd like to thank Sir Mohali and DST for funding, and my students, in particular Sanjit, who is my PhD student who finished last year, and whose work I am presenting today. So just a minute, I'd like to see. Yeah. All right. So because I know we have a lot of teachers, right? Yeah. So I know that we have a lot of teachers here, so I'd like to just urge and also campaign for Aisar Mohali, and many of you might be aware of Aisar Mohali, and many of you may not be. But let me tell you that as far as science is concerned, like technology, everybody knows IITs. As far as science is concerned, IISers are also very good. Okay, they are at part with IITs. Ideally, that is the notion that we developed, Center of Excellences in sciences also, different science streams also, in particular physics, chemistry, mathematics, biology, and humanities, mainly these 5 areas. So we have now total about 8 IISers in different states, and the admissions happen through GEM and also Inspire Fellows. IISer also has their own entrance tests. So please, I request you to encourage your students to take advantage of these institutes and also apply, for different programs that we have in our institutes. So in ICERS, we start from BS level, bachelor's level. So we have a joint bachelor's and MS program. We also has integrated PhD. We don't have only MS program. We have integrated PhD, which means that if some student has done BSc elsewhere, apply for an MS and PhD degree. And for each department, we have about 6 to 7 seats only. So this is highly competitive. But the advantage is that they save about 1.5 years while doing PhD. And then we have regular PhD programs. All these, BSMS and integrated PhD and PhD programs are highly rigorous, and they also deal with cutting edge research in these fundamental subjects or fundamental aspects. For example, even for BSMS students, if they join, there are few requirements which is very distinct from other places. For example, they have to complete 2 summer projects and 2 inter projects before they finish the 4th year. So which can be done inside ICER or which can also be done outside. And nowadays many students do it outside, and not only outside our institute, but outside India also. For example, 2 of my students who are in 4th year, one has recently come back from Israel, one has come back from Germany. So this is very good. The exposure, in terms of exposure for the students, is extremely good. And the 5th year, they have to do a complete 1-year project, which is research-based project. They have to write a thesis, and many students actually, when they finish their work, they write a small paper also. So you see that since our pursuit is developing excellence in basic sciences, you see that by the time a student finishes master's degree, they have a fair bit of idea what research in basic sciences is. They are familiar with different high-tech instruments. They are familiar with the philosophy of research. There's a big difference. We often see students doing masters elsewhere and joining here, and students who come from our own streams. Okay, there's a difference in the mindset because they start doing experiments in the lab in BSc or an MSc in a college or university. So it's a one experiment one day, but here when you do research, we have to start thinking, as you know. And this process, this training actually finishes in BSMS itself if they do it from ICERS, one of the ICERS. And as a result, they also have very good demand as PhD students, India as well as abroad. I think in our case, most of the students go abroad for doing PhDs. And also people who come for integrated PhD and PhD programs, they have been doing excellent. They're getting very good postdoc positions, and then many of them has joined academia in good institutes, and some of them has joined industry, and some even had developed the startups. So I'd request you to spread this message, also to us, request you to encourage your students to explore the possibility of joining ICERS in future. So this is ICER Mohali. This is you can see this gate, and this gate is quite popular. I mean, quite recognized in our locality. So you can see the library, a fantastic library which works 24/7 during exam days. Okay, and this is completely AC. About 800 students can sit there. It's completely residential. So we have hostels here. You can see hostels, and across the road you can see the classrooms. So you see that most of the students, they spend time either in the classroom or in the laboratories, and then they go back and they sleep. It's very beautiful and very nice campus we have. This is one of the classrooms, and you can see the lecture hall complex here. Mohali is a beautiful city. So in particular, I request you you encourage your students to join ISER Mohali. So in my group, our basic emphasis on developing functional nanomaterials. So here I have simply in a very simplistic way, I have divided into three different categories: organic catalysis, electrocatalysis, and photocatalysis. All of them are somewhere connected. When we talk about, you see, all of them are basically catalysis. So the process remains the same. The only thing that we have to think about is that what activates the reaction and what is the reactant. If the reactant is an organic reactant, then we can call it organic catalysis. And electrocatalysis can also be done organic catalysis, but it is normally done in aqueous media. As you know that organic solvents or organic reactants are not electrically conducting. So when you talk about electrocatalysis, it's mostly in aqueous medium, and our emphasis is to use develop highly active nanomaterials which acts as an electrocatalyst for hydrogen generation, for example, or fuel cells or batteries. I think all of you are familiar with batteries, and fuel cell is another technology which complements batteries. In fuel cells, we need catalyst, which is precious metal-based catalyst such as platinum, okay, or palladium. So we make such catalyst, and we also work on photocatalyst. Okay, in photocatalyst, there again in photocatalyst, when we talk about sustainability, one of the important thing is to develop fuels. Okay, and in both electrocatalysis and photocatalysis, we try to generate hydrogen fuel because hydrogen is the most efficient fuel available. So when I talk about any fuel, basically, for example, petroleum, the energy comes from the hydrogen. Petroleum or kerosene or anything you take, any fuel, it has methanol, it has hydrogen and carbon. So carbon is actually carbon energy negative. It takes away energy, but only the hydrogen which gives energy output. So if you take out all the carbon, so you're left with only hydrogen. So hydrogen is the best fuel that one can possibly think of, a chemical fuel I'm talking about. So we try to develop catalysts for hydrogen generation in electrocatalytic and photocatalytic ways. The last thing that we want to do is that we want to take some pollutants, and many of you must be researchers and may have experience in photocatalysis. And one of the most widely used probe to test the photocatalyst is the degradation reaction. So I'm not sure if anybody knows about it, but very briefly, these dyes which are used in our daily life, for example, in our clothes, in your house, in car, everywhere. The thing is that the dyes are very cheap. So nobody tries to recover them. If they are not cheap, nobody will use it. The second thing is that they are very robust and they are very stable. Okay, if you go to a dye company, they will always try to make the dye better and better, more stable and more stable, so that it lasts for a long time. And as a consequence, when these dyes are thrown into the environment, because they are cheap, they are thrown. Nobody cares to recover them. So they become pollutant because they are so stable and they do not degrade easily. So dye degradation was a very important field for about last 50 years, and it is also a very simple research, because when a dye degrade, you can see it with your eyes. Okay, so some of our labs are very expensive and rich, some of the labs are poor. So this is a research that even a poor lab can do, because you can take some dye, and when it degrades and you see that the dye is gone, so you know that your catalyst is working. And you can also know how fast the dye is degrading, how fast the catalyst is working. So many of you might have such experience, dye degradation. I think this is one of the most well-studied experiment is dye degradation. And one particular dye everybody uses because we want to keep the experiments conditions similar. That is rhodamine B. So we also work with rhodamine B degradation, but with a slightly different perspective. Rhodamine B is a pollutant, but when you degrade it from water, for example, so the water becomes pollutant free, gets rid of the dye, but it is the case that it converts to carbon dioxide or carbon monoxide. So it is not carbon neutral, and so the pollutant goes from water to the air. That's what basically is done in the process, which is not good. So I think ours is the first group who are trying to convert it to something more useful. Okay, and this is, for example, one of our papers which has recently come out, that you see this is a, I think I can use a pointer. So these are different dyes, and you see that we can convert one dye to another dye. Okay, I'll go into the details, but the primary results have been published very recently. This has also been patented. So this dye, which is very cheap dye, okay, which is about 2 rupees per gram, has been converted to another dye, which is very reactive, and about 2,000 rupees per gram. So this is a fantastic example of I think, developing photocatalytic nanomaterials. The second aspect, then, when we come to sustainability, is that when you have a catalyst, the idea is that the catalyst must work for many, many days or months or years. So this is a catalyst. So if you see this plot, this is 30 cycles. Okay, one cycle is roughly 1 day. So this catalyst we have used for something like 30 days. And this has worked. In fact, this is a catalyst which always improves. Normally you talk about catalyst which goes bad over a period of time. Now you can look at this catalyst which actually improves with time. So this is just another example in photocatalysis that we have given when we talk about sustainability, that a catalyst which must work for a long time. An electrocatalyst, for example, in fuel cell catalyst, again, platinum. Even when you talk about sustainability, and when we talk about the vision, 2050, India's vision 2050, if we want to be self-reliant, you see, we are going towards, for example, electronic vehicles. Electronic vehicles are two types. One is fuel cell vehicle, one is battery vehicles. As of now, you see that most of them are battery vehicles, but it has certain problems. For example, you need for charging, you need long time. Okay, fuel cell vehicles can be charged very fast, maybe within 5 minutes. Okay, so and most probably we have now fuel cell vehicles in India. Now, coming back to sustainability, when you develop a fuel cell, fuel cell has oxidation reactions and reduction reactions. Okay, reaction is very simple. H2 plus giving water. Okay, it's a very simple reaction, but this reaction doesn't happen. You see, even if you just mix H2 and O2, it will not give you water because it has a very high activation barrier. The reaction is very slow. Okay, and so therefore we have to develop catalysts. So these catalysts are very expensive catalysts. Platinum, for example, platinum is in all the cars, fuel cell cars. Last week, the first bus was released by Government of India in collaboration between CSIR and one private company. So it's a hydrogen fuel cell car bus, and this has this catalyst, and this catalyst cost is about 60% of the fuel cell. So catalyst must work for long times. Okay, and so we also develop catalyst which works for which we also try to check why a catalyst goes bad over a period of time, and then we try to develop how to improve the stability of a catalyst. As you can see here, just one of the schematics, we make these nanowires. They're like hairs. You can see here, they are like hairs. Probably, for example, if you go bathroom, you'll see that sometimes the bathroom sink is clogged because of hair. But this is also very interesting because if you have nanowires, which is very long, okay, so they interdigitate and they give very high mechanical stability. And in this way, we can improve, for example, we can improve stability of a catalyst. So there are many other methods. I have told something very simply, but overall, we work on electrocatalysis, photocatalysis, and organic catalysis, and we try to emphasize the word sustainability. So in today's talk, waste plastic and how to convert waste plastic to something useful. So I'd like to introduce to three very interesting properties that we have discovered in our laboratory. The first one is, I would like to call them breathing. That means it can take oxygen and it can also release oxygen, and it can do it in a reversible manner. And then second thing, second very interesting property is something called autophagy. Autophagy is self-killing. Okay, autophagy is the process of aging. Okay, when a person ages, this happens that the old cell dies, and then the same thing is used to make new cells. Okay, and so we have discovered something similar. It is not exactly autophagy, but you will see what it is. And then we're going to discuss about hypoxia. Again, something completely new. Hypoxia is again related to blood, which means reduced oxygen level in blood, in molecular, in hemoglobin. So, and I think intentionally we kept all these things in biological terms. I think they are used for the first time in chemistry, breathing and autophagy and hypoxia, and in connection to nanomaterials and catalysis. So these three papers, if anybody is interested, they can look at them. So last 2 years we published these three papers. So I thought that I borrowed these slides from a talk which I gave to students, and so I think there are 3 or 4 questions I made up, which will keep help us keep focus on the talk. So the first is that because we want to define new material properties. Okay, can a material breathe, which means BREATHE, it's a spelling mistake. So uptake and release oxygen like hemoglobin. Okay, and here is a plot. You see in this x-axis we have time, and the y-axis we have oxygen content. Okay, this is a water solution containing nanomaterials. Okay, and you can see actually we can decrease or increase the level of oxygen, okay, using nanomaterials. Okay, this otherwise also happen. I'll tell you the details But what I am going to tell it, we can actually increase or decrease or control the amount of oxygen in water in an aqueous solution by using nanomaterials. So can we use waste for harvesting limitless solar energy? That is another question. And you look at this picture. In this picture, what I show is that this is a reaction in my lab. That this is, you see here, plastic. Okay, this plastic was collected from the hostel mess, and it was converted to solution of nanomaterials, carbon nanomaterials. And here you can see this is the recovered part. Okay. So these are nanomaterial powders. So the point here is that you essentially start off with something which doesn't have color, which is transparent, okay, and it gets converted to something which is colored, which means that when something is converted, you know that it is absorbing light. So you know that it responds to solar energy, okay. And then next we have to figure out how this response to solar energy can be used, to carry out reactions. Well, and now I'll tell you what I'm going to show in future is that first we show that oxygen harvesting happens. It breathes, it takes oxygen, and it takes light. Now I have oxygen and I have light activation, okay, of the nanomaterial. This is the same nanomaterial I'm talking about in both the cases. So the next step is, can we use air to do oxidation reactions? We might have a lot of chemistry teachers today, and you know that oxidation reactions are not easy, and we have to use something like H2O2, KMnO4, or K2Cr2O7. They are toxic or they are corrosive, and you have to dispose of KMnO4. What is important is that there is no substitute to it. Okay, they are very simple reactions. We use it every day, but when you talk about aqueous medium, there are not real substitutes to this kind of oxidizing reagents. So our idea was, can we use free air for oxidation reactions? Okay, air is free, but this oxygen cannot be used for oxidation reactions because the oxygen molecule, the oxygen-oxygen bond is very strong. So, and first, that's the first reason. So we have to break the oxygen molecule. We need a lot of energy to do this. The second point is that oxygen solubility in water is very small. Okay, it's just sufficient for fishes, but it is not. It is very, very small. I'll show you how much it is. And this, a reaction becomes fast when the reactant concentration is high. If the reactant concentration is low, the reaction is going to be very slow. And that is one. And not only the concentration, the diffusion also. Okay, if the reaction gets over, the oxygen from air will not go very fast. So whenever you do an oxidation reactions, even if using a catalyst, we must do gas purging, oxygen purging. So the idea was that can we replace it with something else, and we can use simple air for doing oxidation reactions. Another question we wanted to pose is that if we want to use photocatalyst for cleaning water bodies, for example, this is a canal, and you can see it has pollutant dyes. Okay, these dyes are very stable, and it will not go away. It will go with the water. It will go to the undergrounds. It will go to the rivers. It will go to ocean, but it will not die. It will just stay there. So one of the idea was that if we can use some photocatalyst, and because these canals or these water bodies are exposed to sunlight, okay, and we are not in a hurry. If we put some photocatalyst, if they can clean these water bodies, okay. So this has been an old dream, about 50 years old dream, but it doesn't happen because if you put some photocatalyst, there is no way to remove the photocatalyst. Okay, you can throw some few kilos of photocatalyst, and a whole canal or it's a river, but it will remain there and it will eventually settle down. So it itself becomes a pollutant. So, so can we get rid of this problem? All right. So at the end today's talk, okay, I'll just show you rather pictorially. I'll show you that this photocatalyst that we have developed, you say it takes about 1 month time, and this photocatalyst degrades itself. Okay, it goes away from the solution. So a term that we call it autophagy, like what we see in our in living cells. I think we are familiar with the term photocatalyst. It has two terms. One is photo means light, and then catalyst. So any material which responds to light and then uses light is energy, and we know it is very high energy. Okay, how to give you in terms of something like 1000 degree. Okay, suppose you're heating a solution 1000 degree, that is equivalent to something like 0.1 volt. Okay, 1000 degrees equivalent to roughly 1000 degrees roughly equivalent to 0.1 volt. Okay, now if you take sunlight, okay, sunlight is equivalent to something like, it can be any time between 1 volt to 3 volt. You see, so just compare with 1000 degree to sunlight. Even compared to 1000 degree, it is much higher energy. Okay, because of the frequencies, you know, energy is related to a frequency or wavelength. Okay, light energy has very small wavelength and very high energy. So this high energy, if we can convert, okay, and then do a catalytic reactions, okay, then the reactions will be very efficient because we are putting a lot of energy. And we know that in natural photosynthesis, similar things happen. If you combine CO2 and water, it forms glucose and releases oxygen. That's how it releases oxygen. Can we do something similar? For example, can we mix CO2 and H2O and gives, you know, for example, methanol or methyl or formaldehyde or ethanol? Okay, this is called artificial photosynthesis. Or if nothing else, if you don't put CO2, as I told you before, it is the hydrogen which is responsible for energy. Can you simply convert water to hydrogen? So you might have heard many news that there are some cars. Almost anybody can make such car. Any mechanic can make, which runs in water. Okay? So this is not something great. Something is great as far as the mechanic is concerned. But essentially, what you are doing is that you are electrolyzing water to give hydrogen and oxygen. This can be set up by using two simple, pencils. Pencils has graphite rods, so they are conductors. If you connect to them a power supply, and if you give sufficient energy, hydrogen and oxygen will form. This hydrogen can be put into a fuel cell, and you can run the car. Now the question is that it is not sustainable if you are putting more energy to develop to get hydrogen than you are getting it from it. Now you see that here is a semiconductor. Okay, so semiconductor has this semiconductor means there is a homolumo gap, or there's a gap between conduction band and valence band. They are like insulators. Okay, and when we talk about metals, metals has valence band and conduction band. They overlap, so they have free electrons. But in semiconductors, you don't have free electrons. So if you consider the y-axis is energy, okay. So this is the valence band. This is the conduction band. Or in chemistry, this is similar to HOMO and this is similar to LUMO. Okay. Now, when you put light, these electrons get excited. Okay, and you see how the energy from the sun has converted, to something, energy in the sun converted to energy, converted to the nanomaterials. Okay, the electron transferred to the electrons. Now this electron is energetic. Okay, it is, as I told you, much higher than 1000 degrees centigrade. Okay, it is highly energetic. Now this can be used to carry out a reaction. Okay, so this is a photocatalyst. Okay, and then I'll talk something about plastic, and because we are going to use plastic in this particular talk, we are going to deal with plastic. I think all of you already know that the plastic is terrible thing. We generate a lot of plastic, and most of the plastics are non-recyclable. More than 70% of plastic is non-recyclable. So they becomes pollutants. Okay, they remain in the landfills and they become microplastics. And reports that these plastics eventually become part of the food chain, and it comes to our food and eventually to our body. Okay, and it creates God knows what. We still don't know what is going to be the effect, but certainly it is not good. It's not good for soil. It's not good for animals. We know that. So plastic is a problem. So, and many governments by now has tried to reduce the use of plastic, including India. I think this year, sometime on June, they have stopped. India has stopped use of one-time single-use plastic. So, what are the solutions? See, plastic has created plastic is a part of human civilization, growth of human civilization. It's an integral part. We have developed because we have been helped by the use of plastic. Okay, they are indispensable. So it is not using is not a solution, but it is better if we can find this. There has been a lot of effort, in particular last about 3 to 4 years. There has been a lot of efforts from scientists. It can be converted to something useful again. Say plastic or polymer comes from monomer. For example, can we get back the monomer? Okay, is there a way to get back the monomer? But additionally, one of the solutions has been about last 15 years that they are using plastics in construction. Okay, for example, roads. Okay, because plastic do not degrade, the road becomes if you they're put in large quantities in road, and the road becomes very stable. But that is not a solution. It is only quick fixing a solution. That is not a real solution. So there are also another effort people are trying to convert waste plastic to something like biodiesel additives. Okay, and you see, last about 1 year, several important reports have come that how it can be converted to small organic molecules, which can be mixed with petrol, for example. You know that we add methanol with petrol, okay, or with kerosene. Even the petrol we use it about 20%. So can we use something like biodiesel, create some similar molecules from plastic and mix it with petrol? I show you one last example. I think, and then this is all of us know microwave. I think we have microwave in our homes. So microwave, the science behind microwave is, I think, plastic, the way it works. This microwave was used to deconstruct plastic, carbon, and hydrogen. So one very important paper has come in 2020. Was published in it. So what they show is that some iron, basically, okay, if you put some iron oxide and if you mix it with plastic, and if you put it in about less than a minute, the entire plastic will contain and that carbon, the remaining carbon becomes very interest carbon nanotubes, and hydrogen separated out, and it can be used as a fuel. So this gives a good idea because we have some good feeling that probably at least partially by being be able to solve this. So last we're also discussing many other things in the introduction itself. What we are is that can we convert waste plastic to carbon dots? So carbon dot is how to define a carbon dot. We all know dot, okay, and the carbon dot is a dot made of carbon. So when we talk about dot, the idea comes to our mind that it is something small. So, and then when we talk about nanomaterials, so the size of the dot is about few nanometers, say about 5 to 10 nanometers. Now look at this picture. If you see this picture, this is a solution of carbon dots. Now if you look under a microscope, you will see that you can see the scale bar. This is 50 nanometer, and this these carbon dots are about 5 to 10 nanometers. Okay, so 1 nanometer is to roughly tell you 1 nanometer is 1 billionth of a meter. Or for example, if you take your hair and cut it into 1,000 times, 1,000 times, you'll get about this size. Okay. The thickness of your hair, if you divide it into 1,000 times, you'll get roughly this size. So it has just few carbon atoms, few in the sense it has about say 5,000 carbon atoms. Okay, and 5,000 carbon atoms is not very big, because when you talk about 1 liter of carbon or 1 liter of CO2, for example, or carbon monoxide or carbon dioxide, we talk about 10 to the power 23 molecules or 10 to the power 23 carbon atoms. So if you compare this one, each particle you'll have only 5,000 to 10,000 carbon atoms. So very small in size. So it also has functional groups, okay, and different functional groups such as OH, COH, epoxy groups, etc. There are the smallest functional groups. Anybody who is familiar with organic chemistry, if you say functional groups, whatever comes, almost all groups will be there. Something like OH groups, COH groups, CO groups, etc. Now the question is why color comes. This answer is not very clear, because carbon is black. Okay, it is certainly not carbon color. And then what is the origin of the color? Okay, in a very hand waving way, we can say that color is because its band gap has increased, because it has become very small. Carbon has no band gap. Carbon is conducting, so there is no band gap. That's why it is black. It absorbs everything. Okay, when you make it small, the band gap opens up, and therefore you see color. But that is this has been rejected in about last 5 years. And the origin of color is that we know that we have many molecules, almost all biomolecules that we use in our daily life is because of color. For example, if you can see here, I am drinking some Coca-Cola, and you see this color in Coca-Cola it comes from caramel, and caramel is also colored because it has organic molecules which are highly conjugated. Okay, highly conjugated. Benzene molecules. Okay, if you combine 2 benzene molecules, you get naphthalene. If you combine 3 benzene molecules, you get anthracene. And this conjugation increases. Okay, when we have conjugated molecules, you start seeing color. So this graphene is like a huge conjugated molecule, an infinite conjugated molecule. But when we talk about carbon dots, this has many such small conjugated molecules. Okay? maybe 10 atom or 20 atom of conjugated molecules, which are ill-defined because every carbon dot seems to be different. So they are ill-defined, but there's a mixture of different chromophores, which gives rise to this color. So when we talk about carbon dot, how to make carbon dots is very simple. Okay, almost anybody can make it from sugar. You can make it in your home if you have sugar, and if you have pressure cooker, it is very easy to make it. Okay, because we need an autoclave or autoclave. So pressure cooker can be replaced by autoclave. Okay, if you heat it in water, sufficient amount of sugar for a long time. In fact, these might also have carbon dot. I don't know if anybody has checked. So, but then, so the question is, what is the challenge? Okay, if you can make it very easily, the challenge. So let me define the challenges. Okay, its separation is very difficult. You make it in water, it remains in water, it is very happy in water, so it cannot be separated. Okay, now if you have, suppose this water has this much amount of carbon dot. If you want to make it in a company and if you want to take it somewhere else, it is not possible to take the whole solution. And sometimes you want to make it in water, but you want to use it in an organic solvent. You want to do a catalysis or something else in organic solvents. It is very difficult to separate. Okay. The second point is that you see, look at this structure. Okay, you see these are stacked graphene layers. Okay, this is like graphite. Okay, but normal cases, if you make it in your home using a pressure cooker, it will be nicely. If you make nicely stacked, its stability is better. So that is the second problem. First problem is separation. And then a very general philosophical statement is that carbon that can do many things. Okay, it can do many things. I am not going to, for example, it is benign, is toxic, so you can put it in our body. So, for example, so it can be used for biology as biological probes. Okay, as of now, when we have serious problems, we put some probes in our body. They are not benign. Okay, they are metal based, metal organic compounds. So this is a molecule. This carbon dots are benign, and they can put in our body. They can be used to check cancer cells in vivo inside the body with very high precision, and then there are many other things it can be done. It can be used to make lasers. It can be used to do photocatalysis and solar cells, for example. The problem is that, see, almost anything that you do using carbon dot, you have a better alternative always. Okay, something is faster, something gives more accurate reading, or something like that. It is carbon dots are roughly average. Okay, and then the question comes, industries, why they should be used if they have another one which is works better. But if you develop this perspective that in terms of carbon materials, okay, so carbon nanomaterials, when you talk about carbon nanomaterials, all of us probably know about graphene, okay, carbon nanotube, and fullerenes. Okay, graphene is fantastic. Graphite very recently got Nobel Prize. It's a single layer graphite. This is an wonder material. Okay. CNTs is again actually most of the technology revolution started almost synonymous with the discovery of carbon nanotubes. Okay, this is fantastic. There are tubes which are at nanometer scale and very interesting chemistry and physics. So this is definitely worth getting a Nobel Prize, but it did not get Nobel Prize because it is not very clear exactly who has discovered it. So there is controversy, and then it cannot be decided who will get the Nobel Prize. And then the third one is fullerene. Okay, and fullerene is something like football. A carbon, 6 carbon molecules atoms making a molecule is the most beautiful molecule. It is stated to be the most beautiful molecule. It is exactly like a football. Okay, so football also has, I think, 60 places where they actually combine. So fluorine also got Nobel Prize. So all this graphene, carbon nanotube, and fluorine got Nobel Prize. So, but we're yet to find something which is very useful for carbon dots. Okay, this should be taken on a on a lighter note. Okay, but then this question can be asked: what can CQD do so that it becomes as famous as graphene, carbon nanotube, or fluorine? By the way, there's another a carbon allotrope, which is graphene. Carbon has graphite and diamond. Diamond can also be made, which I have not mentioned here. By the way, diamond is basically sp3 carbon, so we are talking about sp2 carbon here. So I'll show you how we have converted plastics to carbon dots. Okay. So I'll show you the pictures. I have shown you once. I'll show you again and explain what it is. But I think many of us are familiar with something called graphene oxide synthesis. Okay, graphene. It's a very famous Hammer's method in which you can take a graphite pencil and you put it in some acid. Okay, H2SO. And then you mix it with an oxidizing agent, KMnO4. Okay, and you slightly heat it, and then you put some H2O2. You get graphene oxide. Okay. And this is very so it is not graphene. It's called graphene oxide because of this H and KMnO4, it forms some which, in fact, this is the reason that because of the formation, the graphene layer it expands. The graphene expands, and if you shake it, this expanded layer separate out. Now our method is some similar, but they're not same, and they are not interchangeable also. So we developed this idea looking at the literature, and there are plenty of literature, actually old literature about 40 years old, which shows that if you take a plastic chain, so we started off with polyethylene. Okay, polyethylene is very widely used. I think if you go to this is single-use plastic, very thin polyethylene, usually called as polyethylene, but polyethylene. So polyethylene looks like this. This is carbon-carbon bond, single bond. Now, when you look at the old literature, it says if you mix it with H2SO4, something similar to here. Okay, you see the starting material is by the way different. That's why it is not interchangeable. So if you react with this and this SO3H group, it gets attached to the carbon backbone. Okay, this is carbon. This is same as this. Okay, and this SO3H groups get attached to it. Now, if you keep hitting it, what happens is that this SO2 group and H2 groups gets released. Okay, this is kind of an intermediate step. So essentially, what happens is that from the polymer, you start developing, introducing this double bonds. Okay, now if you continue this process, this will happen again. And essentially, if you started with a single bond, a polymer with having all carbon single bonds, you can develop a situation where carbon-carbon single bond, double bond alternates. Okay, it is not always the case, which is important for us. But if this is what happens, we can get a polymer chain where we have both single bonds and double bonds. And then if we have something like this, okay, if these carbons forms a cycle, 1, 2, 3, 4, 5. If you consider one more CH2, now if you look at these rings has carbon atoms. Okay, now this chain, if it somehow curved like a snake, okay, and if it gets attached to each other, okay, it will form an hexagonal ring or a benzene. And then if this process continues, okay, it is possible to extend this to form a graphitic carbon. And then you see that it is possible to form a graphitic carbon, but what happens is that sometimes this conjugation, double bond, single bond, double bond, single bond, is not perfect. Okay, in some places you have in several single bonds. Okay, several carbon-carbon single bonds will be there. Those places are going to be amorphous carbon. Okay, this amorphous carbon, if you put H2O2, this graphene is very stable. Okay, it cannot easily oxidized. Okay, but when we have single bonds, and if we put something like H2O2, okay, this single bond will be oxidized. Okay, because it's hydrogen, and it will be easily oxidized. Okay, and then these places, you look at this one, suppose this is a small carbon dot, which is perfect, but on these places, okay, in these places, this is only sp2 plus sp3 carbon, which is not crystallized, they will get oxidized. Okay, now as a consequence, what will happen, this particle will fall off, and this particle is a carbon dot. So this is the process we have developed in our group. So you can look at this picture. I can see this is polyethylene. If you mix it with H2SO4, okay, and you convert it to graphene, okay, you can see that this is what I did. Okay, you can convert it to, as I said here, something like this, or graphite. This is not perfect graphite. Okay, this has graphitic regions merged with amorphous carbon where we have a lot of sp2 sp3 carbon. Now if you just put H2O2, these are at all reflux condition, high temperature. Okay, but H2SO4, so it is temperature is about 150 160 degrees. So if you put H2O2, it will degrade. Now does this amorphous carbon will degrade, only the carbon with graphitic regions will fall off. Okay, then you can see here. Okay, this is an SEM image. You can see this is carbon. Okay, and you can see this carbon has become more amorphous after being KMnO4 because of oxidation. Okay, we will not discuss the details, but essentially at this time you get this carbon dots, and you can very easily extract these carbon dots from water, and you get this powder. So the problem associated with separation has been solved. So I'm not going to discuss why we can solve this thing. This has something to do with the solubility. This carbon dots are also soluble in organic solvents. That's how you can extract it. Okay, an organic solvent with low boiling point can be evaporated, and we can get this powder, which does not happen with other carbon dots. So this is essentially what you have is the first synthesis of carbon quantum dots from plastic. What is very important is that the yield is very high. You see, I told you that some of the carbon dots, the carbon which is here will be lost, and they go as CO2. But the remaining carbon is about 70%. Okay, and these carbon are both soluble both in aqueous and organic medium, and stable for years, at least now roughly 4.5 years in my lab. They are stable, and they are soluble in both organic as well as aqueous medium. That's why we can use it in. That's why we can do reactions in organic and aqueous medium. And the purification is very simple. You see, we do not purity issues. Okay, everything converts. The people who work with carbon dots, they know that carbon dot synthesis is very simple. It's very simple, but you cannot get rid of it. It is not easy to get rid of impurities. Or if you want to get rid of impurities, the yield is very small. So purification is extremely difficult. So industries do not go for it easily. Okay, you need to do column or something like this. So people do not go for the industry. Do not go for it. We do not have this problem. It is extremely simple. No special process is required. You have to only extract it with a solvent and you have to just evaporate the solvent and collect it somewhere else, you get the powder. As I have told you, these are about 5 nanometers, about 8 nanometer size. And you look at this microscopy image, you see some lines. If you look at carefully, you see that these are graphitic lines. Okay, these are graphene layers. So this is like a small piece of graphite. Okay, this is highly crystalline carbon, which was another challenge. Carbon dot is not easy, but so we have been working for about last 1 year. Now we have been able to convert polyethylene or polythene. So we have been able to convert about 10 different plastics of different types and to make these carbon dots. So you have seen that this is actually the actual globe which we have used to convert these plastics to carbon dots. This is used in the kitchen in a hostel. So yield is very high. We know crystalline. Purification is easy. A less amount of solvent is used if you consider with any other species. Okay, the amount of solvent used is very small, and purification is very easy. The standard methods of purification of carbon dot can take up to 2 to 3 days, and about will take something like 5 liters or 10 liters of solvents, because you want to add something called dialysis or column chromatography. So next, now we know about synthesis part. I'm going to discuss about oxygen first property to explain. And I also told that we briefly discussed this, that oxygen concentration is very important if you want to do an oxidation reaction. And that's why a real oxygen is not good, because its solubility and diffusion, okay, is very low, most of the solvents. And let us look at the process, how a reaction happens. Okay, this is a catalyst, and we know it is much easier to visualize it using a homogeneous catalyst, for example, an organometallic compound, or an organic organometallic catalyst or organic catalyst. So in inorganic, in nanomaterials or heterogeneous catalyst, it's more difficult, but still roughly we have a surface on which oxygen will come and sit. This oxygen has to be activated. Okay, this oxygen is not active because oxygen double bond is very strong. So this oxygen has to be activated. For example, if you can push one electron into this, okay, if it takes one electron, it will form a superoxide radical. Okay, O2 dot minus. Then this will become weaker because that extra electron go to the LUMO, okay, lowest occupied molecular orbitals, lowest unoccupied molecular orbitals. So if you look at the bond order will decrease. So this bond, the oxygen bond will decrease very relatively easily. So then if this one breaks, this oxygen is available for oxidation reaction. Anyway, I just want to tell you, see, graphite is used in fuel cells. We have discussed fuel cells or something like several times now. And I also mentioned that H2 plus O2 giving water is the fuel cell reaction, primary fuel. And graphene or carbon is used. One of the reasons is that the carbon absorbs oxygen. Okay. If we want to convert oxygen to water, first oxygen has to be there in the catalyst. Okay. And graphite or graphene absorbs oxygen. The question is where? And the answer is that graphite is or carbon is never perfect. Okay. If you look at this crystal, in material there are lots of defects. In those defects, oxygen sits there. So carbon can absorb oxygen. Okay. And that has been known. sorry. And then it has functional group presence, and the functional groups are also supposed to assist oxygen absorption. So that's the reason that we check oxygen level in the carbon dots. Okay, we are the first one to check this, by the way. Now I'll cut the story store and I'll show you how to look at these figures. Okay. This is in the y-axis we have oxygen concentration, and this is something time. Now this is a water solution. Okay, a water solution containing carbon dots. Now please remember that this is 25 ml water, and this is 25 ml with 25 mg of carbon dots. So 25 mg and 25 gram. 25 ml is 25 gram. So in terms of weight percent, it is only 0.1%. Okay, so this has 0.1 weight percent of carbon dots. Now look at the oxygen level first. Okay, what has happened to the oxygen level? In normal water, the standard about 300 to 320 micromoles. Okay, just look at the saturation level. Okay, about 320. This is this with tiny amount of this one. It has gone to, it has become double. So what it means that if you have a water and if you have a carbon dot solution, the amount of oxygen essentially doubles. And this oxygen, where does it come from? Okay, because we have a solution with a high amount of dissolved oxygen. The question is, where does it come from? Okay. Now, I talked about a breathing. It's a phenomenon called breathing. This is nothing like breathing. What happens is that if you pour some other gas, okay, in water also, for example, if you put CO2 gas or if you put argon gas, this CO2 or argon is going to replace oxygen, right? The solution is going to be filled with argon or CO2. The same thing happens in this solution also, but with some certain very important differences. You look at this, okay, you look at this, first of all, this amount is different. Okay, now look at this blue one. Blue one is we are purging nitrogen. So oxygen is going away, you see, oxygen is going away. Oxygen level is almost zero. When you take oxygen, this CQ2 solution, it never goes to zero. It is still about, say, 120. Okay, however amount of argon or other gas you put it will never go to zero. It will be something about 1. The second important phenomenon you see, it takes about 10 minutes to come to about 90% of the saturation value. Okay, which happens in about 4 minutes here. Okay, despite the fact that this is a higher number, so it absorbs oxygen very fast. Again, I'll cover certain things, but I'll give you the final results. Okay, which means that about 1 gram of carbon dot contains about, we have calculated this, carbon dot contains how much oxygen. Okay? 1 gram of carbon dot contains about 0.01 gram of O2, which is equivalent to 1 oxygen molecule in 250 carbon atoms. Okay, which is roughly equivalent to 1 weight percent of the carbon dots. So this carbon dots, this extra carbon or extra oxygen must be associated with carbon, right? And then we say that if you calculate it, about 1 weight percent of oxygen must be associated with carbon, because the rest of the water, you see, this is only 0.1 weight percent. Okay, rest of the water is free water, just like the other water. Okay, the extra oxygen is coming because it must be connected to the carbon dots. If you calculate this one, it's say about 1 weight percent of CQDs. Or if you say if one carbon dot or CQD takes about 125 to 130 oxygen molecules. Okay. Now compare this with hemoglobin. Hemoglobin has about 2 weight percent. So this is very, very high amount of oxygen on material. In fact, if you, there's another kind of research where people develop materials which absorb gases. Okay. Now, if you, there are also materials developed for oxygen absorption. for example, zeolites or metal organic frameworks or MOF. Now this is a room temperature measurement. If you compare this with a room temperature measurement, this amount is actually very high. Okay, this is compared to even MOF or zeolite. This is an extremely high amount, and this is comparable to hemoglobin. Now, we can also see that this amount actually increases with the amount of carbon dots. Okay, the more the carbon dot we put, the more the amount of oxygen. And you see that it is like breathing; it can go down and come back, and go down and come back. It is repeated. It is repeatable. This happens. So, which means that oxygen-carbon bond is a weak bond. Okay, and this oxygen is not coming from carbon dot itself. Okay, so this must be coming from oxygen is harvested or sucked in from air. And this is also very important because reversibility is very important, because if you want to do a reaction, essentially the carbon dot becomes a vehicle. Okay, we will take oxygen from air, activate the reactant. But as soon as it has given to the reactant, okay, now it must take another oxygen. Okay, you see this reversible process. It takes, it gives, and this is what also you see in this. Okay, it gives, it takes, it gives, it takes. So this repeatability is important if you want to do chemical reaction. So I'll skip this one. I mentioned that there are two things which are bad in organic in using air as an oxygenant. That one availability. The other is the diffusion coefficient. Okay, it diffuses very slowly. Okay, and because it doesn't form very strong hydrogen bonds, and at room temperature, for example, this diffusion, if you use a very tiny amount of carbon dot, that is 0.1 weight%, the diffusion coefficient improves by about 4 to 5 times. And that's why, because it comes from air, okay, it comes from air, this, what happens is that if you remove it, okay, this enrichment is very fast near the interface. Come from air, okay, but if you go down, it is much slower. Okay, you can see it here, these two plots, but essentially it goes to the same value over a period of time. Okay, in water, same thing happens, but the reaction, the diffusion can become very fast. This oxygen, it goes and picks up and comes back. Okay, we can explain at the end of the topic if somebody is interested why the diffusion is faster based on a fixed law. Now I'll show you what application, how it can be used for oxidation reactions. Okay, and so as I told you, carbon dot takes about 130 oxygen molecules. Okay, and you know that it absorbs sunlight because it is yellow in color. Okay, and so the idea is that if we can replace or KMnO4. So what happens is that H2 or KMnO4 it react something called ROS, reactive oxygen species, which can be something like OH dot or OH. Okay. Now what happens is that you consider this is a carbon dot and there is an oxygen molecule sitting on top of this. When you shine light into it, these electrons get excited. Okay, this excited electron can be transferred to the oxygen. Okay, and then it can form a superoxide radical. Okay, this superoxide radical can take a proton from water. Okay, forming OH. Okay, and then OH can break or form OH, or it can take one more hydrogen and form H2O2. Okay, so there are various ways. Okay, that H2O2 can form, or H2O2 or its related reactive species can form. They are called reactive oxygen species. And when you actually do oxidation reaction, these species are responsible for a reaction. So it is possible to do this using carbon dots because it has large amount of carbon dots. sorry, oxygen. And if this oxygen gets used up, it will take another oxygen. Okay. And I have already showed you the motivation behind looking at this. And we told that there is a problem that if we use photocatalyst for doing this reaction, it itself becomes a poison or polluted. Now, the other point is that it has to be degraded very fast. Okay. Now, this is a rhodamine B dye. You see from water, this peak shows rhodamine B is there, and this peak is missing means rhodamine B is gone. Now you see that the rhodamine B has gone within 16 minutes, a fixed amount. Doesn't matter what amount it is. You can see here the color is also going down. Now, 16 minutes, if you compare with literature reports, okay, this is fantastic and this is very, very good. Okay. And so that was the first interesting thing that we observed, and but it was then we later realized that it is because it has the oxygen atoms. Okay, it is extremely good compared to anything that has been known so far. The second point I told is that a catalyst must be used for many, many times. And here is a plot. You see, this catalyst was used for this reaction for 100 times. Usually people check it for 5 times or 6 times, and this has been used for 100 times. And it is still very, very active compared to something like TiO2. The first cycle of TiO2 is a benchmark catalyst. It has been known for years, about 50 years now. And this reaction was discovered using TiO2. So this is extremely good compared to even TiO2 first cycle. Okay. Now the point is that this has gone down. Okay, and this has gone down because of something called autophagy, which I'll explain later. Now we know that we can actually maintain this reactivity also. I'll show you the second example, and then with these two examples, we'll stop the reactions. Okay, these two reactions are called this oxidation of alcohols or oxidation of amines forming this azo compound. Now, when you look at the literature, you see that these are again model reactions and has been studied thoroughly. Now, when a photocatalyst is used, you look at the papers, you'll see that always oxygen purging is used for these reactions. The reason is that the solvent will have less amount of oxygen. And it's very well known that reaction is slow. But oxygen purging is not good, because if you want to, again I bring the concept of sustainability. If you want to use oxygen, then oxygen has to be separated from which is it has to be separated, it has to be transported, then it has to be used. So it's a long process. Okay, so that's why the idea of using air in this case. So now look at these reactions. I am showing only for this reaction, and this don't worry about this slide. I'm going to tell you what only the things which is important to be seen. You look at this reaction, this one and this one. Okay. One is done in air, one is done in oxygen. What is interesting here is that essentially there is no difference in the conversion. Okay, so it means that whether you use air or whether you use oxygen, you get the same efficiency. And the reason is that because it already has oxygen, we don't have to purge oxygen into this. I can also show you this one, for example. If you use it in nitrogen condition, okay, if you use it in nitrogen condition, you will still get oxygen. You'll still get the product, because I showed you that the difference with water and when we discuss the breathing property. Even if you purge it with nitrogen, all the oxygen will not go away. It will still have about 20 to 25 oxygen molecules per carbon atom. Okay, so therefore, even if you do it under complete inert condition, you will still get product. Okay, with 100% selectivity. Okay, and this is impossible to get, as far as I know, using any other catalyst. this is a substrate scope. Let us not discuss it, but we can extend it to other different compounds. So I just wanted to show you this. This table was made about a year back. I have not added new reports. But if you look at that time, okay, this reaction is done at room temperature. Okay, you look at, see, many of them are done at high temperature, and this is invariably almost everybody uses an oxygen atmosphere. Okay, you look at the reaction time. This is 1 hour, and it takes longer time. Okay, this is the reactant. You see most of reactant than what we use. Okay, similarly, the catalyst is also ours is on the smaller side. Despite the fact that we have small amount of catalyst, more amount of reactant, less, but it takes less amount of time to convert. Given the fact that this room temperature is on in here. Okay, so this is, I think, again, I have for last 6-7 months, but that was at that time by far the best catalyst for these reactions. For both the reactions we discussed, and based in the sense much better than whatever was known before, despite the fact that we use only air, not oxygen. So what it means is that we can get rid of, such a setup where from air we generate oxygen, or something like high pressure autoreactors. Okay, and then we can do it in a simple system. And this is very important for sustainability if you want to use, and in particular if you want to use a photocatalyst, you cannot use such a system anyway because this is not transparent. So you have to build a reactor which is made of quartz, which can withstand high pressure, and but using the carbon dioxide we can avoid such situations, and we can use simple air. So the second point I'm going to discuss, and very briefly, is something called autophagy. Okay. So I have explained that if you put at least here, it is going to be a waste. It is going to be a pollutant. I'm trying to hurry it up because I see that I'm exceeding time. Okay, but I'll hurry it up. So what happens is that you look at this slide I showed you before. If I put these carbon dots in air, in sunlight, this carbon dots completely goes away. Okay, and these carbon dots, if you put it in dark, nothing happens. It takes, in this case, about 38 days. In all the slides, I am keeping the concentration shapes that you have a feeling. Okay. Now we see that this happens to all the carbon dots we made from 10 different other plastics also. Now the question is that why this happens, and yes, okay. So we discussed that when we have oxygen molecules, it develops this ROS, right? And we discuss this ROS is the one which reacts with a reactant. The thing is that the thing is that what happens?
I request participants to mute themselves. I request participants to mute themselves. Gautam, I'm sorry. Let me just try and mute this gentleman. Yeah.
ये चप्पल घाल चल खड़े हो चप्पल है ही वाली घाल ऐकत जागा परिश्वरी काही पण नको बघू मोबाईल.
Yeah, Professor Gautam, now you can continue. I'm sorry about it. Looks like some participant unmuted. You are not audible. You are not audible. I think you are also muted. Looks like, is it? Maybe one of the participants tried to mute everyone. Yeah. Okay. So can you unmute yourself? Besides the camera, there is a mute button.
Audible?
Now you are audible. Please go ahead.
Okay.
Sorry, these are perils of online. Yeah, and people have families. We have to accommodate.
No problem.
That,
No
yeah,
problem. This is dinner time.
These are
I
teachers.
think
These
the
are
kid
faculty
must be
members
hungry.
from different colleges. Yes.
Yeah, the kid must be hungry. So he can also join. No problem. Please just mute it and
Yeah. Thank you.
problem. So we discussed this ROS happens, and this is the reason for oxidation reactions. Now, what happens if this gets generated but no reactant? But a reactant is also something like a molecule having carbon, right? So if there are no reactants, what happens is that very briefly, it attacks itself. It attacks another carbon dot. Okay, it attacks another carbon dot. Carbon dot is stable, but stability is a relative term. Okay, carbon dot is stable. That's why it takes 38 days, but it is not, eternally stable. Eventually, it gives up, and it converts to NH2. So in fact, you can see here that there's a plot. We have checked it. Okay, if you leave it without reactants in light, CO2 will start forming. At the same time, the level of oxygen will go down because this oxygen and carbon will combine to form CO2. So as a consequence, this is what we have seen. If you keep it for a long time, all the carbon dots will run away. So what we mean is that we come back to this figure again. If I put my carbon dots here, first of all, this carbon dots will not settle down. Okay, they will be swimming there. So they will be harvesting sunlight. And then they will degrade these dyes. Okay, once the dyes are degraded, they are fine. Nothing will happen to them. But once the dyes are over, okay, then they will eliminate themselves. They will not create any problems. Okay. For example, you can see here, okay, when the dyes are there, it is fine. Okay, after 10 cycle, almost it has maintained the reactivity. Now there are no dyes. If you just expose it to sunlight, okay, 11 cycle, you see that the color is also gone and the reactivity is also gone because of autophagy. Okay, last topic which I'll explain is something called hypoxia. Hypoxia, as I explained, is the low level of oxygen in our tissues. So, but they are very interesting. This is more like a company talk where I want to sell my concept. But question when you talk about scientifically talking is that what happens to a reactant concentration on a catalyst surface? Okay, well, and nobody knows this answer. I have checked it thoroughly. Nobody knows answer. We know everything when this is not in strong light. Okay, we know something about reactants when we measure light, but in typical sunlight, okay, when you put, so actually nobody even cares whether the reactant concentration remains same as that in a room light or in the dark, or does it change? But this is very important because we know that reaction depends on the concentration. And we are talking about the concentration on the catalyst surface, a photocatalyst surface. The photocatalyst is active to light. Okay, it reacts with light and its electronic structure changes. Okay, because electrons get excited. So there is every possibility the reactants sitting near the catalyst active site is going to change. But this has never been checked. Okay, I found some papers about 30-40 years old papers, theoretical papers discussing this, but then it has never been followed. So what I'm going to show is that this is something that I wrote with my son's pen because our paper was not rejected several times by the editor. So one night I was very upset and I wrote this with a pen and took a photograph and sent it to the editor. And then he said that he will send this paper for review. So what I showed here is that if you take water molecule, if you put light, see the oxygen level remains same, 330, 330. Okay. But if you take a CQD solution, okay, if you put light, okay, this will go to something like 5. Okay, this value will become 520. Bottom it will remain at 650, top it will become 520. You see, there's a gradient. Okay, and this gradient is not small, it is about 20-30%, right? And then instead of a white light, if I put different lights, okay, if different lights of different frequencies, I can get different values. Okay, so what I can do is that I can have a solution and I can create different oxygen levels in different regions. And please mind you that the diffusion of oxygen is very slow, so you can actually maintain this difference. Okay, you can maintain such a difference for a long time at room temperature, no problem. This cannot be done in a normal solution. It can be done in a carbon dioxide solution because the carbon dioxide responds to light and the oxygen level changes. So if you remember this question, what happens to a catalyst reactant concentration under light? If you consider oxygen is a reactant, you see that the level of amount of oxygen reduces now. And this is not very difficult to understand. Again, I'll very simply tell that it has more amount of oxygen in dark, less amount of oxygen in light, and that happens because the excited electrons interact with oxygen and repels it. Okay, oxygen has a lot of electrons, and this if it is in certain positions in the carbon dioxide, it doesn't get transferred to oxygen. Instead, it repels oxygen. And this is a repeatable process. Okay, if you switch off the light, again it will start taking oxygen. You see this again. I come back to this 650. Same concentration. If you do it in light, it will become 520. You see the amount is small. If you see in water, the amount is same, 320. Now in dark, okay, now you expose to light, okay, see the amount of oxygen is going down. Now you switch off light, again it is picking up oxygen. It will go to the same value, okay, if you wait sufficient time. It takes 6 to 8 hours time. Okay, it depends on the interface region. So you can see here, this keeps happening repeatedly. Okay, in 10 to 12 years it will go back to the original side. So this is something where we have termed as light induced hypoxia. Okay. We have confirmed that actually oxygen is getting dissolved. Okay. So essentially what it means is that you see the oxygen comes from this side. Okay. And light, if you put light from this side, first oxygen removal will happen from the top. Now if you put the light from the opposite side, oxygen will dissolve from this side, and diffusion of the dissolved oxygen is slow. So the oxygen landscape is going to be different. Okay, this is just a proposal just to show that if you have two beakers and if you put light from two different sides, you will get theoretically at least two different rate of the reactions. Now the sensitization of this is the UVB spectra, you see, of carbon dots. It absorbs light from about say 500 and onwards. Now this oxygen level, okay, this oxygen level, you can see the oxygen level also depends on the excitation. Okay, the more the light is absorbed, the less is the amount of light. Okay, maximum light absorbed, it takes about 420 to 450. So essentially what it means is that I have already told you that if we have a beaker like this, if we put light here, see, in this part of light we have less oxygen here, and here we have more oxygen. And then if we take different lights and if we make a landscape, something, if we put, put lights like this, okay, in this, then we will also have different kind of oxygen levels within the beaker. And I think as a chemist, this is fantastic. I never thought that something like this can happen, but we see from our experiments that this is possible. Okay, so in conclusion, I have shown that we can convert plastic to carbon dioxide in a very efficient way, and the carbon dioxide we make has very good proper synthesis wise. It's very sustainable compared to the previous other known methods. It shows oxygen harvesting, it shows oxygen enrichment, it shows improved oxygen diffusion. We can use ambient air as free oxygen. Okay, it shows spontaneous elimination, which we call as autophagy, and hypoxia or oxygen gradient or landscape creation in a solution. So I hope that if we started off with this, not so serious question that what can make CQDs as famous as graphene, CNT, or fullerene. I don't know, but if we find some more interesting things, how to use this landscape, for example, do cascade reactions or something like that, I think this is a very exciting phenomenon. With this, I conclude. I'm sorry, I think I have taken more time. And if you have any questions, I'll be happy to answer. I know that this is dinner time.
Yeah, thank you so much, Professor Gautam. And actually, this was one of the reasons why we decided to keep only one talk, because it is better to do certain things in detail rather than quickly rush through two different topics in a single day. And it's also like the evening time. So for most of the teachers, like only today was Sunday, rest of the days are weekdays. So they would be coming after their regular classes and schedule. So it becomes more difficult. So I will invite if there are questions.
Sir, hello, sir.
Yes. Yeah, please
Yes,
go
sir.
ahead.
My name is Anil Pandya, and I am a PhD scholar in PDU Gandhinagar. Sir, my question is, any temperature effect you observe in the CQDs?
In terms of what? For which property?
Sir, as a you shown some self resisting, or that's term you use, self killing or CQDs
Self
effect.
Yes, yes.
Yes.
Actually, no, we have not checked that. The reason is that sunlight anyway we cannot use this reaction in lab because we cannot engage the light for 1 month. So we have done this experiment in actual sunlight, and Mohali is hot, and so the temperature outside will be something like close to 50 degrees. And this experiment was done at around 45 to 50 degrees. So you put it in the morning and take it in the evening, take it back. So we have not checked the effect of temperature. I'm sure there will be some effects.
Thank you, sir.
Yeah, other questions? So, Professor Gautam, I had a question. Like in the initial part of the talk, you had shown the work on plastics to like basically conjugated structures, right? So can we go to that slide? Right. I was curious to know, like typically these conjugations or cyclization that happens in high dilution synthesis. Right. Classically, if we look at the process of aliphatic going into aromatic rings, right, that requires a high dilution, means low concentration of analytes, which will kind of go into cyclization process. So, however, here, if I look at the entire process, there was no requirement for any high dilution. Like it was done at reasonably high concentration,
Right. I
right?
think so.
So,
Yes.
like, what is your take on that?
Yes, actually, this is happening pretty much as you can see here. Just a minute. It is. You see that we start with plastic and we convert it. Uh,
Into some kind of an aliphatic chain, right?
so yeah,
Some
so you
kind of
can
a
see
long
here,
chain.
you have an experimental proof that it
Hmm.
has become actually graphite.
Hmm. Hmm. That's right. So it really
So,
raises questions into like why we should relook into this macro cycle formation. Like
so
there has been a lot of uh,
this is the proposal that I have given. I think I skipped this one. I did not show it.
uh,
Is that you see first these lines? This is a polymer, and then you have double bond. Then you have more double bonds. Then you have many double bonds. Then you have two possibilities. Okay, one possibility is that intramolecular. Okay, this is intramolecular, where first one benzene will form, then the second one will again cyclize, and the third one will form. So it will keep going like this.
yeah.
The second possibility is that intermolecular. You see there, this is one chain, this is one chain. They are not the same chain. Here it is the same chain. It is giving this graphene. In this case, this is intermolecular, and we do not know which one is actually doing the job. But if you see this second one, there is no problem. Actually, this is good if we have close proximity, because it will simply convert more easily.
Hmm. Yeah, so no, so I understand, like so you had explained even while you were talking about it. But if we look into classic textbooks, right, of macrocycle formation, they're always pointing at high dilution synthesis approaches. So here, this is one such counter example, right, which is very, very interesting, where one doesn't have to look at um, like primarily any kind of
Okay.
dilution issue, and still you get
There is
cyclization.
there is one thing we have to make a distinction between strong bonds and weak bonds.
Mm-hmm.
Anything which eventually come out of weak bonds, something like hydrogen bonding or pi-pi interactions, something like macromolecules. I think probably they also depend on weak interactions. In this case, they will form very nicely if they go slowly one by one. They will go and they will not come back. Eventually, the structure will form over a period of time. But in the case of strong bond formation, I think that may not be necessary.
Mm-hmm.
Even harsh condition and this condition should be fine.
Yeah, and in fact, the FTIR, the topmost
Ah,
image, that very clearly shows that there is significant OH functional group as well as COOH and OCO, right? Classic graphene oxide type of a
yes,
FTIR,
yes. And
right? So this
then
is
the
this is
CH2,
very, very
the hydrogen
interesting.
is
Very,
gone.
very interesting. Yeah, very, very
This hydrogen
interesting.
is gone, and
Hmm.
then you can see the Raman spectra. It is graphene. You can look at
Hmm.
XRD. XRD also
Yes,
clearly
yes,
sees.
yes, yes. And that too, like the D peak is reasonably weak here. Like G peak is
Yes,
primary. So that's
yes,
very exciting to see. Yeah, thank
yes.
you.
So in
Thank
fact,
you. It gives
in
me
fact,
some ideas which maybe later on we can discuss.
yeah.
Hmm. And
We are trying to
similarly,
now use
huh,
this.
huh,
We are trying to see if how we can use this carbon itself, because
huh,
I think, as far as carbon is concerned, apart
hmm,
from high surface area carbon, there are many other carbons which again India imports. So in this
right,
context, we are checking now.
right, right. Okay, thank you. So, like why I was mentioning this is a similar type of possibility is there. See, we are doing a part of our work on biomass gasification,
Uh-huh.
right? So the residual part after gasification, whatever is the solid, like
Mhm.
that can also act as a reactant or like getting into this kind of a cyclization process. So that would
Okay.
be like total usage, like from waste to value. Not only we work on the
Okay.
energy part, but also later on materials
Okay.
part. So that's one interesting problem among several. Yeah, I will talk to you about it later. Thank you so much. So are there more questions? Are there more questions from the audience? Fine. So people who are part of this FDP, like they are request as participants, I would request them to fill the Google form. I think we have already sent you a Google form. Let me just retype it. So in the chat, you will find it. In the Teams chat itself, you will find it. So please go ahead and fill this Google form. Yeah. So Dr. Nirmala Devi is saying no, sir. So we have just posted it again, so you can check it wherever you have typed no, sir. Yeah. So please fill that, and then like we will kind of. Yes, yes, Kashti, please go ahead if you have a question. You're not audible clearly. Can you just type your answer in the chat? Type your question in the chat. Are there any other questions? Because it's quite late in the night, and even our honorable guest, he would have to leave. Right, so is there any other question? No, I cannot see anything in the chat right now.
Okay, maybe it is dinner time. It's Sunday.
Yeah, that's right. Yes, can you please post your question in the chat? Because the internet at your end is very, very poor. We are unable to hear you. Everyone is waiting.
Anyway, I'm also available in email. Anybody wants to email me, they can email me. I can send my papers. And I'll again request everybody that please send your good students to us. We want to make.
Yeah, seems there's no, like, not really getting back.
There is something else. Would you explain what switches the breathing of carbon dots? This is very simple. Suppose the reason oxygen binds to carbon is because the weak electrostatic interactions between oxygen and the carbons. The same almost any material, dipole interaction or quadrupole interaction happens on any material and any gas. So, for example, if you fill this room with oxygen, you'll eventually find that some oxygen molecules will be sitting on the surface of these walls. Similarly, if we fill this with carbon dioxide, you'll see that walls are covered with carbon dioxide. The only question is, what is the strength, interaction strength? Okay. Now, suppose this room, if you fill it with oxygen, some oxygens will be on the walls. Now, again, if you fill it with carbon dioxide, those which are sitting on the walls, the oxygen molecules, will be kicked out, and they will be occupied by carbon dioxide. The same thing will happen. So this repeats. So I think breathing is not something, anything special. Any material, suppose if you put your hand in water, it will be covered with water. If you put in air, that water will go, it will be covered with air. So the same thing happens. But one important distinction is that the interaction of oxygen and carbon is strong because of the high the other groups of surface function groups which stabilize this. I have not calculations which stabilizes these oxygen molecules on the carbon dot surface. So it is very easy to take it out, but it will put large amount of nitrogen, for example, or argon. Then again, if you stop purging nitrogen or oxygen, nitrogen or argon, again oxygen will come from the surface. From it will slowly diffuse. Argon will, and it will take oxygen because oxygen bond is stronger with than nitrogen. I hope answered your question.
Yeah, it's fairly clear. Kashti, like, is it fine?
Thank you, sir. Thank you, sir. But sir,
All right.
one thing I would like to say, as you shown the graph there. So there particularly what is switching, just like in firstly what's happening, the oxygen concentration is increasing and after that this falls. So why is it falling? Whether that is because of light, you switching light on and off because of that or something, it's happening with time or automatically.
I think, sorry, I think I have misled you. There are two things I have seen. That switching I have shown in presence of light. That is only light effect. The hypoxia effect is light effect, which I showed later. The first time what I showed, and hypoxia effect is less, 650 to something like 520. The other effect which I have shown, and we compared with water, is that it goes to 640, 650, something like 130. That happens because you purge it with nitrogen or argon. So if you purge it with nitrogen, all the oxygen will go, so it will become something like 35. In normal water, it will become almost zero. Now, if you just stop purging nitrogen, it will start taking oxygen from the air slowly by itself. And in about 5 to 6 minutes, it will again regain all oxygen. And same thing will happen in water also, but it will take 10 minutes and it will carbon dioxide, it will reach.
Okay, thank you so very much.
Okay.
Thank you. Yeah, thank you, Kashti. So if there are no further questions, let us thank the speaker. So here we are giving an online applaud. Thank you, Professor Gautam. So maybe we'll kind of stop this session. Yeah.
All right. It was pleasure being with you all, and best wishes to all. Bye. Bye. Good night.
Yeah. Thank you. Bye bye. Good night.
Bye.
Okay. Thank you to all. Thank you.
So fine. Tomorrow we will meet again at 7. And tomorrow speaker is going to be Professor Kotnala. He's going to talk about like further into this domain of green energy and how novel materials really help achieve that. So see you tomorrow.